who's going to talk about galaxy evolution Kit-Survey.
Okay, I start. Hi everyone. I will start with some thanks. I thank you to be here for this special occasion, for this special event for Massimo, and also I hope you have enjoyed. You will enjoy the conference, also the beauties on Napoli. So my talk is about galaxy evolution within the Kit-Survey. Already in the last days, Magda and Mario have introduced the Kit-Survey within VST. Here is a fast summary, but I will just say that Kit aims at studying different topics from gravitational lensing, galaxy-galaxy lensing, the distribution of dark energy, dark matter in the universe by means of weak lensing, galaxy evolution, which is the topic of this talk, the search of galaxy clusters, and also high redshift quasars. Of course, within the eighth twin survey, which is the Viking survey on VISTA telescope, will provide a long wavelength baseline to analyze galaxy evolution. Why Kits for galaxy evolution? Of course, for its properties, the area covered, the depth, and the seeing, but we can see by these images why Kits. Here I compare our airband our airband image for a galaxy, an example of galaxy, on the left, on the right versus SDSS, which is of course one of the most important modern survey, probably the most important in the optical regime. You notice of course the larger fraction of sources detected, and also the quality of the structure. Here are other examples. Mainly look at the top. You see what is a merging event. You notice also the quality of the image, the details, the arms. And faster than light. Here is this is the status of Kit-Survey, and here is the DR2 data release 2 of Kit-Survey. We have completed around 12% of the total survey. I start with discussing our project from the selection sample for our analysis. We are extracted from these DR2 kits 22 million of sources using Sextractor, of course. Using morphological criteria, we are left with 7 million of galaxies. And finally, we have operated this criterion on the signal-to-noise ratio, and we are left with 450,000 galaxies with the best photometry, since we are going to perform a structural parameter estimation for this sample, and we need high-quality data for this. Here is just a picture for a summary of our data sample, where I plot the observed color as a function of redshift. Of course, in our sample, we have a lot of galaxies from different kind of types, from red galaxies to blue ones. A fundamental step in our analysis is, of course, the determination of photometric redshift, since our survey is a photometric survey. We just have used the optical photometry to derive photometric redshift using two different kind of methods. The standard one, which is the set-fitting method, which consists to fit to the colors empirical models, and the other one from Massimo Brescia, Peppe Longo, and Stefano Cavuti, which consists to use a machine learning method which is not dependent on the assumption of any model in the spectral fitting. So for a subsample of our galaxies with the spectroscopic redshift measured, here I show you our derived photometric redshift as a function of spectroscopic redshift. We have used an area with spectra from SDSS and gamma in common with our fields. What you see is that, of course, here you notice the scatter in the result from machine learning method, which provide high quality photometric redshift, which are ideal for galaxy evolution analysis. Not here, on the contrary, the scatter in the case of set fitting. The reason is that this kind of procedure is able to not account for bad photometry, since training by the training of a spectroscopic sample. So I will use this redshift for all our samples. Okay, stellar masses. We use aperture photometry to derive, using stellar population synthesis model, the stellar masses, assuming a Chern mass function. Here you see the completeness of our sample as a function of stellar mass. Here, is a function of being so redshift from galaxies redshift smaller than 0.1 to a larger redshift. What we find is that we are complete to a redshift of 0.5 at masses larger than 2 × 10⁻⁻⁻ solar masses. Okay, this is another nice picture where I show the stellar mass as a function of redshift, colored by the color, observed color. Here again, the region where we are complete. Finally, structural parameter in this description of our data production. Structural parameters are fundamental in our galaxy evolution project. In particular, we use this environment to default from Francesco La Barbera, which allow us to determine in an automated way structural parameter for a large number of galaxies, and also fastly. In particular, using fitting to the optical photometry of kits, a static profile, taking into account of PSF, and also, of course, deriving all the structural parameters. This is already tested in previous work. This is an example of the output of our procedure. You see on the top left the image of a galaxy, on the right the residual, in the bottom the residual at different angle from the center, and on the right the different parameter we can estimate with this kind of analysis, the standard structural parameter from size, Cersec index, position angle, and so on. Here is another example. Also here you notice how the program is successfully able to detect any substructure we can see in the residual on the right. Few slides. This part is about scaling relation, dark matter fraction. We are going at the end of our one of our aims is to investigate scaling relations in galaxies, and also the dark matter content in the central regions of galaxies. I will leave it here to compare our results for kits with the same result for a sample of local galaxies, which is from SPIDER. This is a survey which uses SDSS EU kits data, but I will limit here to a sample of galaxies with the measured optical SDSS photometry in this, of course, this redshift beam. And for this sample, structural parameter using to default, which is the same code we have used in our case, is adopted. The sample of galaxies in our kits, DR2 release, is this one in common with this sample. I compare here the access ratio, SPIDER versus kits, and the most important sizes, and also Cersec index. Of course, there is a good agreement within a scatter, which is related to differences, of course, in photometry. More important is a scaling relation. I have adopted the standard cosmology to convert the observed scale in size to the physical scale. Here you see the Cersec index as a function of size, so size versus stellar mass, the size-mass relation. There is a good agreement, except with some differences due to larger sizes in kits. Another piece of information in this kind of analysis to understand galaxy evolution is the analysis of central dynamics in galaxy. To analyze central dynamics usually people use the Jeans equation to derive the radial velocity dispersion. We assume an L-band Cersec profile for the light profile, a simple model for total mass profile, which is an isothermal sphere. Solving this equation, we take the radial velocity dispersion, we project along the line of sights and within an aperture, and we compare with the SDSS aperture velocity dispersion, which have, since we are using spider galaxies, which rely on SDSS data, and the final output of this analysis is the dark matter fraction here, which is, in this case, I plot the ratio between the total mass to the stellar mass within the effective radius, and Claudio Marasson was discussing in her talk before this kind of quantity. And here are the results. These are typical results in this field, with dark matter fraction increasing with size, stellar mass, and velocity dispersion. Here, the two samples, and there are some differences, as you see. Finally, this is the final part of my talk about the search of compact galaxies. Already, Bianca was discussing about this in her talk. I have found this nice picture to say some words about galaxy evolution every one of us knows about. What is found at larger redshift is that galaxies are very compact, massive and compact, usually with a size smaller than 1 or 2 kiloparsec. By means of redshift, of merging minor and major, these galaxies grow up to become the big galaxy we observe in the universe. But the question we can do is, but we can find these compact galaxies at lower redshift. So we can find at lower redshift this kind of systems. And we have tried to do this with our DR2 releasing heats, imposing particular criteria, so this compactness criterion. We are searching for very massive galaxies. Sorry, I will be fast. Yeah, galaxies with the best 2D fitting, and finally to remove any contamination by stars, since we are searching for very small systems. So stars which are misclassified. In this case, we are using Viking data, Viking photometry, and we are plotting the stars and the compact candidate on this diagram, a typical color diagram, which allow to separate stars from galaxies. And we have taken this sample of final candidate. This is some picture with the image and the residual. Here another picture where I show the color as a function of redshift for our sample. The red points are our candidates. If you remember, I have shown you that we are complete to this redshift, so we limit to the galaxies, to these compact candidates at a lower redshift. And finally, we compare with simulation and with the other data, the density. We are going to calculate in bins of redshift the density in the volume, comoving volume of our galaxy. And compare with two results from semi-analytical models. The model from De Lucia Blasot provide larger density. In this model, they take just in account those galaxies which have increased in mass of a fraction smaller than 30% of the initial mass and 10% of the initial mass. These two are, sorry, yeah, we lost, sorry. Yeah, these two results are from some recent results in the literature, which have found at most one system, so a very low density, which is not consistent with prediction from simulation. And these are our results. Of course, in this case, I'm plotting just the full sample of galaxy, with independently of the age. As the first analysis, we have used for the moment optical photometry to provide an estimate of age. Of course, we need to improve the analysis, adding first near-infrared photometry and spectra. So it will be needed a spectroscopic follow-up, not only to provide an estimation of spectroscopic redshift, but also provide precise stellar population parameter. But this is the dashed lines are the result from those systems which are older as galaxies at redshift, which was born redshift ZU2. Finally, okay, in our case, we don't find any candidate at this, which is statistically consistent with this result. But what I have to stress that there are other works, as the one from Bianca Poggianti, which on the contrary provide a very large density. So this is important since to understand this discrepancy, to understand the evolution density of this kind of system is important to understand the role of minor mass in galaxy evolution. This is the last slide, just to say you that we are going to have at the end of our survey a sample like consisting of 3.5 million of galaxies with high signal-to-noise ratio, for which we are going to analyze structural parameters, stellar mass, color gradient, and so on. And with a sample with a coverage of SDSS spectra, we are going to analyze dynamics in the central region, dark matter content, initial mass function, the mass profile of galaxies. Finally, I want to stress that probably with this big sample of galaxies, we are going to have one of the biggest sample with measured structural parameter in the U, G, R, and I band at redshift smaller than 0.5. And thank you for the attention.
Thank you very much. Questions?
Just to clarify, the mass limit that you're using, 8 times 10 to the 10, is much higher than the one we use. So if you want to compare directly, we can tell you what the number density is in the PTGC for your limits and your definition of compactness, but they cannot be compared with space value.
Yeah, this was the reason of the question I made you. Probably we were fast, I was not able to understand. The point is that I have taken this result from this paper from Quilis et Trujillo, which state that this is using the same criteria from Trujillo et al. 2009. I use it just for this. Of course, the reason, yeah, if you confirm me that this is assuming probably a mass larger than 3 per 10 to 10 solar mass, something like this, of course. Okay, it's okay also for me. I feel more comfortable with this. And yeah, of course, you have found a larger number of compact candidates. Yeah.
Any questions?
So the comparison you showed, the dark matter fractions you showed, this was, so you had spectroscopy for those, is that right? So,
For SDS, from SDSS.
Yeah, so this was SDSS.
Okay. Everything is, yeah, I'm just using SDSS spectroscopy and structural parameter from kids we have determined with 2D code, and the ones from the spider survey.
So for the proper kids area, where do you get the spectroscopy from? Is this all follow-up proposals, or how? What are you envisaging there?
Our main idea is to search for region overlapping with SDSS or gamma, for example. For the SDSS, of course, is our main, probably, yeah, that is our main. As I was saying, with matching with SDSS, probably we'll find something like.
How large is the area? I mean,
the overlapping region. The moment. Yeah.
This is 150. So for the moment we are just 150 square degrees, so we have a limited. But I mean, of course we're using public data for the moment. We know that this should be something more, so we can discuss about it. Of course, I mean, it's not time to follow up, spectrally follow up the Kitzler for the moment, not yet. Rather than gamma, of course, but it's too low resolution to do this kind of work. So we're looking for synergy with other spectroscopy survey to get going with this kind of analysis, a larger area, of course. All right. So let's get to the Next speaker, let's take again Congresso. Next speaker is Chiara Spinello. Talking about the low mass and the initial mass function in massive ETGs, little galaxies.
Okay, thank you, Nicola. Thank you, the organizer, for having me here and give me the opportunity to say happy birthday, Prof. I was one of the lucky to have Massimo Capaccioli as professor during my undergraduate. And I'm also lucky because I grew up in this beautiful city with amazing weather, amazing food. But then I moved to the Netherlands for 4 years, and now I am in Gushing, so the weather and food went down for me. So let's get started. This is an overview of my talk. I'll show you how to constrain the low mass end of the initial mass function directly from optical galaxy spectra. And I spent part of my talk explaining you the method I'm using. And in particular, we're combining strong gravitational lensing and dynamics that gives us constraint on the total and even stellar mass within an aperture. And I'm combining those results with those information with spectroscopic simple stellar population models. So far, we've been using line index measurements, but there's a plan, future work plan, to pass on full spectral fitting code, in particular collaborating with Claudia Marston here in the audience. And the result is indeed that the low mass end of the initial mass function seems to varying with galaxy velocity, stellar velocity dispersion of mass, if you want, if one assumes a universal cutoff mass. And I will show you and explain why this is important, and so far it's been so hard to understand this point. So if the IMF is basically, well, everybody knows what the IMF is, but what not everybody realizes is that when people working on very massive early type galaxies are constraining the initial mass function, we really put in constraint on the low mass end of the initial mass function, because everything else is dead. So every single star with a mass, let's say above 1.5, 2 solar masses, in a population of 8 gigayear or older, is already dead by now, okay? So the only part of the initial mass function that I can put constraint on by looking at the very massive galaxies, and the very massive red and dead galaxies, is this one, okay? And this one will be described by a slope, this x parameter, but to be completely fair and honest with you, I'm in this work, and in most of the work, except for La Barbera tool, everybody's always assuming a single power law to describe the IMF. And as you can see here, you have a 1.8 power law, which is often called Chabrier IMF, but I would rather call it Milky Way-like, because it will give you a mass-to-light ratio equal to the one you will get assuming a broken power law, Chabrier power law, or Krupa if you prefer. Salpeter having a slope of 2.35, and bottom-heavy, Roy and Van Dokkum IMF, with a slope as steep as 3 or as steep as 3.5. Okay, so this being said, another important point that often is not made is that by changing the low mass end of the initial mass function, we're actually changing by a lot the mass, the cumulative mass inside the galaxies, but we're not changing by a lot the luminosity. Actually, luminosity constraints are coming from stars with masses between 1 and 5, 7 solar masses, to be really conservative, whereas we're changing again the low mass end. But this is dramatically changing our mass-to-light ratio. So, by looking at spectra, can we really count? Can we really say something about those M-dwarf stars that are, claimed to be more conspicuous in more massive galaxies? Yes, if we can find tracers, spectroscopic tracers of this population. So this is one of the most famous lines, the sodium doublet, around 8190 angstrom, which has been used in a Nature paper to claim that the IMF was not, the low mass end of the IMF was not universal, and this is another famous line around 1 micron, the Wingfold iron band. And as you can see, for different population, for different type of stars, we have no line in this region, no assertion line in this region, with the exception of the M-dwarf, which show a very strong absorption line. So if you can measure those line index, so just the strength of those lines, of those IMF sensitive lines, then you can actually count M-dwarf, therefore you can constrain the low mass end of the IMF directly from galaxy spectra. You have to pass through simple stellar population model in order to study the behavior of those features, in particular those are optical features, those IMF-sensitive features, and you have to study their behavior as a function of age, different colors on those plots. as a function of abundance, either metallicity, alpha to iron. If you're lucky enough to have incredibly beautiful data, you can even trace different elements. And of course, IMF slope, going from a 1.8 to a 3.5 bottom heavy slope. As you can see, both those features are increasing with IMF slope, and they are, they depend on age as well. And for the TIO2 feature, as well as all the TIO molecular features I'm having in the optical spectrum, the equivalent width is also increasing with increasing alpha to iron, going between 0 and 0.4, so alpha enhanced population. But as Claudia told us, massive galaxies seem to have alpha to iron, seem to have higher alpha to iron, whereas KH1 is showing the opposite behavior. So it's increasing with IMF, but it's decreasing with alpha to iron, and it's almost independent for age if you set yourself for a population older than 9 gigayears. So if you can produce index plot and try to basically, let me skip this and show directly this, and try combination of index that have sensitivity to different parameters, for instance IMF and alpha to iron that goes in opposite direction, then you can break the generacies, and when you put your when you measure line index in your integrated spectra of your galaxies, then you can eventually put constraint on each parameters. This is an example using SDSS galaxies, color-coded by velocity dispersion, and here different points are different galaxies. I'm plotting magnesium-iron, which is a combination of magnesium and iron features that has been often used to constrain metallicity or alpha to iron in accordance to the model you're using, and TIO2, which is indeed one of the IMF, or gravity I should say, sensitive features. And the galaxies are moving in this direction by increasing velocity dispersion between 200 and 350 roughly kilometers per second. As you can see, if it was, and those are Corroy and Van Dokkum simple stellar population model, different colors show different alpha to iron enhancements, different lines, different points on the same line show different IMF, as you can read, and everything has an age of 13.5 gigayears. Okay, so as you can see, moving vertically in this plot will change only the IMF, the low mass end of the IMF slope, whereas moving roughly horizontally in this plot will change the alpha to iron. So if your galaxy, for instance, lies here, then you will infer a population of 13.5 gigayears, roughly an IMF slope of 3.0, and the solar metallicity and alpha to iron. By the way, everything has solar total metallicity, and I'm just changing the alpha to iron abundance by changing color. But I'm kind of cheating here, because I'm plotting a single age population. When I'm going to plot a 7 gigayear population, blue showing again solar metallicity and solar alpha to iron, red showing again an alpha enhanced model, then you will see that you will infer for the very same galaxy, an IMF of 3.5. And if you make your model older, obviously, then you will infer a bottom lighter IMF. So the first take-home message is the following. We really need a lot of indicators. We need blue indicators that are roughly IMF insensitive to constrain age, metallicity, and alpha to iron, and at the same time, with the same characteristics, same signal to noise, same instrument if you're lucky, we need redder indicator, because M dwarf are emitting in the red part of the optical and the infrared much more, to constrain the IMF and to be sure to break all the degeneracies between the indicators. That's exactly what we have been doing in the latest couple of years, I would say, and ended up in a paper just published last year. And we find very promising features in the optical spectra. It's convenient to use optical because simple stellar population models are much better, if you allow me, Claudia, in the optical, and we found a lot of features, and we perform model galaxy comparison by stacking the SDSS galaxies I've shown you before in 5 velocity dispersion beams, and we compared with a very broad range of simple stellar population model. In this paper, we only used Corroy and Van Dokkum models, but we have another paper which is under revision that perform a detailed comparison between the Muscat model and the Corroy and Van Dokkum model, Muscat model by Valsakis et al. And those two models really differ in the ingredients, isochrons, everything is different in those two models. Even the way they deal with metallicity is different, but we still find a very the same answer. So we compare model with we compare SSP model with galaxy spectra with very high signal to noise. In a chi-square sense, we obtain a best fit IMF slope for each for each expected spectrum, and as you can see, the IMF, the low mass end of the initial mass function, seems to steepen with velocity dispersion. So that would be a sort of an L-star galaxy, and again, those are just elliptical galaxies, early type galaxies. This would be L-star galaxies, and that would be a Milky Way-like IMF with a slope as steep as 1.8, whereas this will be a very massive early type galaxies that will better match with a salpeter IMF slope. And that's, by the way, the relation we infer. If you want to compare with non-spectroscopically based results, for instance, the one obtained by lensing and dynamics, or even dynamics by the Atlas 3D team, then you have to translate your IMF slope, which is not really a physical parameter, into a mass to light ratio. And in particular here, I'm plotting the mismatch parameter, which is nothing else than the ratio of the mass to light ratio you will have, stellar mass to light ratio you will have with the inferred IMF slope from simple stellar population studies in my case, divided by the mass to light ratio you will infer by assuming a salpeter IMF. And those are the same points I was showing you before, and the black line is the line we fit. And different colored lines are different studies by La Barbera et al. Using again simple stellar population model, but the other set of model. Treo et al., as I said, using lensing. Corroy and Van Dockum using my same model, but with full spectral fitting. And finally, Cappellari et al. Are the red points. And obviously they are spanning a wider range of velocity dispersion, and also they're not restricting themselves to elliptical galaxies. So we're comparing apple with bananas. But still, a clear evolution of the low mass end of the initial mass function is found if you move between 150 km per second and 350 km per second. So this is my second take-home message. The IMF slope is indeed varying. It's not universal, and its low mass end seems to steepens with velocity, with stellar velocity dispersion. As I anticipated, this is just one side of the story. So I told you that by using a set of isotons and a set of parameter stellar libraries, for instance, stellar population people are building up the integrated light spectra with this equation, where the phi is the IMF, and so far I've been telling you the story about the IMF slope, but there's another, even more important parameter, which is indeed the lower mass limit cutoff. The higher mass limit cutoff is a function of the age of the population, the stellar population age, whereas the lower mass limit has always been assumed to be universal. And what's really, really annoying to me is that different codes, without telling you, are using different assumptions for this number. For instance, Corroy and Van Dockum uses the hydrogen Barling limit, 0.08, whereas Brusois and Charlotte 2003 are using, I'm sorry, my Italian is popping up. Brusois and Charlotte 2003 are using 0.11, 0.11 solar masses. Obviously, if you're looking at light, so from spectra, you're not going to put any constraint on this number. But luckily for us, we have lensing, and lensing traces mass. So we started, back in 2011, we started the X-shooter lens, I shouldn't say survey, I would say project by now, because we have 10 systems. With the X-lens survey, we are indeed combining strong gravitational lensing and dynamics with stellar population, and basically we are inferring stellar masses from two completely independent methods. The first one tracing the mass, and the second one tracing the light. And we're doing this in a completely blind way. Matteo Bernabé is sitting at his desk in Copenhagen where the sun shines, and as I said to you, I'm sitting on my desk at Captain Astronomy Institute before, and NPA Garching with rain all the time, and we're not communicating, okay? Until we don't finally get the final number, we're blind. And so we take the IMF slope inferred from the line strength analysis, and this is an example published in 2015 on the pilot problem of the survey. This is the most massive galaxies, this is the least massive galaxies we were having at the time. By assuming different values for the cutoff mass, we calculate the solar mass to light ratio using a set of isotons, and by having the stellar population parameters, of course. Taking the luminosity from redshift, or by fitting a luminosity profile to HST images, We compare those results, so the simple stellar population results, with the ones obtained by gravitational lensing. And this is the most massive galaxies. Black histogram is the one obtained by Matteo from lensing and dynamics. And different histograms with different colors are might infer stellar masses by changing the cutoff mass here. So here, this is always 2.6, an IMF with a slope of 2.6, and the red one has a cutoff mass of 0.115, which is Bruce-Weinberg. This one has a hydrogen barreling limit, and this is slightly higher. And here you can see how the situation will change by changing the IMF and keeping constant the cutoff mass. So basically, by increasing the cutoff mass, making it bigger, we will obtain a lower mass, and by decreasing the mass, the initial mass expansion slope, let me skip this and then we get to the result, we will again changing the inferred stellar mass from stellar population. When we have an agreement between the two methods, then we can put constraint on both the IMF slope and the GM law. So far, the generality between the two methods is still big, so we need more systems, but if we put together in a MCMC sense the 6 systems for which we have the analysis so far, we get those results. Okay? So, well, we can do more with lensing than you should. Ask me if you're interested, and that's my conclusion here. Again, I've shown you that the initial mass function is not universal, and the low mass end of the initial mass function seems to vary with stellar velocity dispersion, but this result assumes a constant cutoff mass, and by using lensing, we can put constraint on that too, so stay tuned and wait for future work. And yeah, I'll leave you with the slides, you can see it for yourself.
So the exact limit of the IMF, by the way, I use 0.1, so this is consistent with what you determined. That was what the well-educated school would use. The 0.08 is a bit of a heuristic thing. It would not matter at all if the IMF would not become bottom heavy. Now you can, in fact, notice the differences. I have no idea what was I shall use 0.0115 because I don't remember that. But it should be noted that before the revolution of the last few years, those values over there would not matter at all. And now you can even resolve it, so yeah.
Yeah, you can see from this plot that if you're changing the mass cutoff to a lower value, you won't change the luminosity, or you won't change the spectral at all. I agree with you.
Yeah, exactly.
Completely.
Except in the Gearing planet where you want to measure the indices of the dwarf.
Indeed, yeah. If you read my future work, I want to go to the near infrared because there the contribution is much higher. But Claudia, it's nice to have, sort of a way to explain the IMF variation in other ways, and those ways could reconcile with theory, maybe a little bit easier. Not sure though.
Tom?
I'm getting increasingly desperate, so you should probably just ignore this. But x equals 3.5 or so, and cut-off mass of 0.5. Russell Smith, who does this same sort of work, found that fits. That's what we suggested a few years ago to fit the K20 NZ in terms of a passive evolution that you might need. That, I presume from your graph you would exclude cut-off at half a solar mass and
Yes.
top light.
So, above all, I will completely exclude everything above 3.0 because that will violate the lensing constraint. So basically, with lensing, we're getting the total mass, and we can calculate the total dynamical mass to Rai ratio. And if we take such a bottom-heavy IMF, then the stellar mass to Rai ratio will be bigger, larger than the total mass to Rai
Even if you
ratio.
have a half a solar mass cut-off.
Definitely, you can have crazy cutoff mass, but no. That's a point. That's the generality between those two parameters. But again, you have tracers of so you have equivalent. You have absorption lines that are there only in case of very low mass stars. So for instance, the sodium first, the sodium doublet, it's only strong in stars with masses below 0.5 or 0.4 solar masses. So if you see an absorption in your integrated spectrum, then you have to have at least one star which has a lower mass, and Wingfold band 2. So again, going in the infrared will allow us to count stars per unit of mass.
Okay.
Thank you. This was an excellent talk, but I would like to issue a complaint. I mean, this is not a problem with the IMF. Nobody has ever said that the IMF at masses lower than 1 solar mass is universal. This is a problem with you guys that make models and assume that this is the case. The IMF, as we know it, is universal for masses bigger than 1 solar mass. For masses lower than 1 solar mass, it's all over the place when you actually go and count the stars. So I was wondering whether this is actually a dynamical effect where you're losing stars, the low mass stars, or something else. But this IMFs of slope -3, you don't see anywhere in clusters in the galaxy anywhere. So it's an invention of you people.
I have to disagree. I mean, the fact that you're not observing anything like that in the Milky Way galaxy, it's not.
It's where we observe an IMF. We're
yeah, I agree. But Milky Way is not, and the Milky Way, it's not a massive early type galaxy, and it has not been formed through the same process. So why we have to assume that the IMF is everywhere the same? Although those systems have a very...
You are.
I see your point now. What? No, me. Okay, theoreticians. Okay, I agree. Cosmologists and theoreticians. Oh, then we agree. You were pointing at me. I'm not. I'm far away to be cosmologist.
So, we are last question first.
So you showed these lensing results that asserted in response to Tom that cuts off, say, slope 3. Of course, the lensing results ultimately are a decomposition in mass between dark matter and the stellar component. And I know it's not your piece of it that was evolved from you. But can you comment at all about whether there's any concern about that decomposition and how robust those lensing results are to certain assumptions about halo shapes or anything like that?
Sure, I can comment to that. So let me start with future works. Because we do have some concern, we're looking for Russell-Smith galaxies. So if we can find a configuration for lensing analysis that allows us to probe a very small region with lensing. So if you're familiar with lensing, if we can find an Einstein radius which is smaller than the Einstein radius, right? So we can get rid of the dark matter. We can probe a very central region of the galaxy where we are dominated by baryons, and by only doing lensing model on the old school way, so without dynamics, without decomposition, by just measuring the total mass, we can allow for a 10% of dark matter, but no more than that. Then we can put an upper limit on the IMF slope without bothering about IMF, without bothering about the composition stuff. Then coming back to the comment about those results, I'm confident that we are doing proper work. We're using the state-of-the-art of the lensing plus dynamics plus stellar kinematics code, which is the Cauldron code. And what we're doing is a multi-Gaussian expansion a la Capellari, 2002, but I might be wrong. And we're probing very broad range of anisotropies, and also we're changing the halo inner slope, and we're paying attention to this, but we do have this free parameter. You're right.
Afraid we have to stop this here, but
I'm sorry.
Thank you very much again, Chiara. So it's time for to talk about science with Muse spectrograph.
Yes.
Right?
Okay. So first of all, thank you for the organizer for the invitation. I think it's a pleasure. So I will not discuss about science with the Muse spectra is a bit too large. But I've seen that some of you have already some Muse data, and I hope you have as much as fun as we have to playing with the big data cube. So I will present in view of this meeting what we've done on the Hubble Deep Field South, some first results. So this is work done with many people, but two main contributors are Jarle Brinchman and Johan Richard, and many others. So, but because it's a meeting about surveys, I should mention something about surveys. So then the question can ask us that, do you think that an optical survey with less than 1 million galaxies and a field of view absolutely ridiculous of a few arc minutes is still useful? So if you think no, my talk is done. But I will try to convince that there are still a few things to do with in this sort of work. And the main reason is that image. So the Hubble deep fields are there since now more than 10 years, and they are still the deepest that have been obtained of the far universe. And of course, we've learned so much with them, and not only because of the quality and the depth of the data, but because of the ancillary information that have been obtained on it. One key ingredient beyond this image is of course to obtain the redshifts. And so most of it have been done by photometric redshift, which is a technique that works quite well. Nevertheless, it has its own limitation, as it has been mentioned sometimes. First of all, sometimes it can fail completely. It's not well known how it works when we go extremely deep for faint galaxies. And there is quite a number of information that are only given by spectroscopy, like the internal kinematics and physics of galaxies. So, ideally, what we would like to do is to have spectra of each of these objects. But currently, the limitation of the present survey, spectroscopic survey, is roughly limited to a magnitude of 25. And only 10% of these galaxies are brighter. So we were used that we have to wait for the next generation, the James Webb, the ELT. But it's not true, because we have Muse, and this is what I would like to show you. So, briefly, what is Muse? So, Muse is a panoramic integral field unit, means that it has a relatively large field of view for an EFU, but very small for an imager, 1 arc minute. But a very good sampling and an excellent image quality. It has been designed for this. A large simultaneous spectral range and a medium spectral resolution, and extremely high end-to-end throughput, which is the key. And this is a combination of all that makes Muse completely unique. So Muse from the start, it has also, I must mention, an advanced data reduction package because it produces a lot of data. So from the start, when we answered the ISO call for ID, that's 13 years ago, that was basically the idea that building an EFU with such a characteristic should allow something completely different, which what we've done with the first generation of EFU. That means follow-up or doing detailed study of single objects. We can make EFU that can really go deeper than the present generation. And that's what we try to do. And so 13 years after this call, we had the first light 9 months ago, and already quite a number of interesting results to show you. So I don't go into the detail of the instrument, just to mention it's 24 integral field units. It's a big thing with 24 rate sensitive detector, very optimized throughput, and also optimized to work later with the adaptive optics facility. It's a relatively big instrument for those who have seen the instrument, but it's nearly fit in the UT4 platform, and it's a bit expensive, but okay. So in view of the goal we had 13 years ago, and during the last commissioning run, we make a try on the Hubble Deep Field South, which was at the correct location, with the idea that at the end, to validate such an instrument, it's only by doing. And so, because we want to do this sort of field, we spend some time on it. So, the Hubble Deep Field South has been observed in 2000 or 1999, I guess, and so it was one of the first, well, not the first, but the second deep field down, and there has been a lot of interest, but then there has been the UDF, which went deeper, which was also observed from the north, and for a number of reasons, I think most of people concentrate on the UDF. But I think still an interesting field. It's quite deep. It goes to magnitude 29 or a bit more, and this is the field. So this is the field we've done, the 1.5 minute field within that one. We select this because it had a relatively bright star for the slow guiding system, and one star here which allowed to measure the PSF. So we have accumulated 27 hours on this field during the run of July. So that's the image that is produced, the white light image. So already you can see there's quite a number of galaxies that show up here in this image, and you can see also that the images are very good. You can measure the image quality, and the PSF here, of course, change a bit with wavelengths according to what is expected from the atmospheric turbulence. But nearly, you see, we have a mean PSF of 0.7 or a bit less, and for 27 hours of accumulation, I think this is quite fantastic. And it shows also that really it's limited by the atmospheric, by the thing, so we will do even better when we have the error. So you see quite a number of galaxies on right, that's the bright star. And so we are going to explore that all together. So first of all, I think one important thing is, of course, when you build these instruments, and you have at some stage you will be killed by the systematics, and how far we go. Can we accumulate forever, and so on. And this is the exercise we did, trying to sum up with various exposure and to see how we do. So you see that the square root of 2, it goes very well until 10 hours and start to deviate a bit, but not so much. And that's very good news. That means that we can accumulate and go even deeper. So there was an interesting test to be done. So let's start with a census of the Muse HDFS field. So that's the Hubble I-band image, and what we found. So that's looking really to all the literature. We are surprised that at the end there is only 18 spectroscopic redshift that have been measured on this specific field. So in total, I think there's probably 50 or even more, but they cover a wide area. In a small range, in the dense regions, only very few have been done. So what we measure is that. So we obtain nearly 200 redshift and 200 spectra of all this population. So that, I think, you will see many interesting objects into this field. So first, the obvious 8 stars. A few of them were already identified with proper motion. Let's look to one. There's a nice white dwarf stars showing very well here. You can see the quality of the spectra. I think it's probably in the halo of the galaxy. There's 7 what's called nearby galaxies, the one where this just defined by the limitation that the oxygen 2 emission line is below the blue cutoff of Muse. So these are this galaxy. There's a few relatively bright spiral galaxies there, but the others are very small guys. And let's look to one. So you can see this. So you will see again this image. So give me a few explanations. So this is here the HST image in the 2 bands. That's the reconstructed white light image in Muse. That's the image which is reconstructed in an emission line, if there's any. That's the spectra here with a few identified lines. And in gray, you show the 3 sigma due to mainly the noise due to the sky. And you can see a zoom there. So you see it here correctly, alpha. But this is a very small galaxy. So the magnitude is 25. And that's this redshift. It will correspond to the fairly low mass object. And that's quite many. So one of the main populations are detected with the O2 emission. And they cover this redshift range. And quite a large range in magnitude, including very faint one. So I take an example of a faint one. This is the magnitude 26.7, redshift 1.3, and it's there. And you can see the spectra here. You can see the O2 emission, and given the spectral resolution we have, the O2 is nicely resolved. So there's no ambiguity, and this is very important to disentangle what we observe. So here, the medium spectral resolution is a key, and helps a lot to identify the objects. So we have galaxies that fall in the so-called redshift desert, and which can have only absorption line, and they are of course much more difficult to measure redshift, so probably only the brightest can be measured. We probably have to work a bit more to use the known techniques, but maybe to adapt them to the Muse. But we can find quite a number of these galaxies. And we also found C3 emission galaxies, quite interesting. This one I think is very interesting. You see the carbon 3 is very well resolved. And in that galaxy, we also see Mg2 in emission, which is quite rare. I think it is the only one in that sample. So they show very well. We also find 2 AGN, clearly. There's one here you can see very well. The emission line. This one is really fairly well resolved, spatially resolved. And finally, we found what we were looking for, Lyman alpha emitters, quite many. So 63 Lyman alpha emitter, covering the full redshift range, and up to the magnitude of nearly 30. I show one here. This is a magnitude nearly 28. So I don't see if you have seen many 28 magnitude objects in spectroscopy, but that looks quite nice. You see the Lyman alpha emission line, and when you reconstruct the image in the Lyman alpha line, you see it very well. So what we found, and I think that's very interesting, is that really to find objects with this sort of a technique really helps to have the 3D information, and helps in many ways. And when you see a coherence between the image when you move into the data cube plus the spectra, this is absolutely clear that you can really have a very well known, efficient way to detect objects. So I showed just another one, for example, one which is a magnitude 6.3, nearly 29 magnitudes. You see also clearly well how it shows in the emission line there. And the galaxy is very faint. Okay, but we found something also quite interesting. So we found 26 Lyman alpha emitter, we have no HST counterparts. And they cover this wavelength range, and the magnitude is, of course, unknown. So let's look to one. So this object here, you see there is absolutely nothing in the HST image. And when you look to the spectra, it's absolutely obvious. You look to the Lyman alpha emission, asymmetric, show very well, and if you reconstruct the image in the wavelength, it shows absolutely obvious. We have many of them. We have been conservative and kept only the one we are sure. There are probably many more. I can show you a second one to convince you. So maybe here there's something not clear, but here also you can see. This is a redshift 6. And so we try to estimate the magnitude of this object by stacking the image of the HST, and we found that there should, in average, should be a magnitude 30, but that's of course only an average value. But this gives to this object a very high equivalent width, of course. So that's what we found in total of the population of galaxy. And we started to play a bit with the content, trying to understand. And for example, this is the base for the more nearby object. It's a redshift below 1.3, and well, it's not a surprise that we are really sensitive to emission line objects, and these galaxies are really star-forming objects, as probably as in higher redshifts. We obtained also 20 spatially resolved galaxies, and that was also quite important. I show one. So this is a global property as we have. It's a relatively bright object, 22, redshift 0.6. You can see all the emission line. But of course, the most interesting is that what you can do with that. And it's very nice. So you can really resolve the internal kinematics of the object, at the velocity dispersion, and many more. So there are lots of things to do in this sort of object. And we have 20 of them, and that's going to be very interesting. Just for comparison, it was the same object observed with the giraffe, and you show what the next generation bring you. Really completely different the physical property you will derive from this. Of course, you will, if the message, you will probably identify this object as merger or this, but if you look, they are seem to be very regular. Okay. In a way of playing and fishing in this big data cube, we found that there's many overlapping objects, even at the HST resolution. I give here one example. There's one object here. We found this spectra. It's clearly, obviously, there's O2 line. This is confirmed because there's H beta O3 here, which match well. So that's an O2 emission at 0.8. But there is this line here, which at the end can only be Lyman alpha. And you can see here, probably maybe this is second object, but even in the HTC resolution, you cannot disentangle them. And to have the 3D information is the key. Yeah. So, about the redshift distribution, that's what we had previously. That's what we had from this, plus this one, which is below the HST limit. What's interesting, if you look to the number, so that's we reach a completion of 50% of magnitude at magnitude 26. That means that we are relatively complete, but we do all galaxies within that field up to magnitude 26. We have half of them. We can determine a redshift with high precision. And it's even up to 20% at a magnitude of 28 and 29. So it's quite a difference. And this is shown, well, I just show that we can, of course, start with play with groups and do a lot of studies environment. You can find groups at very high redshift, and very interesting things to do there. I will skip that. Just want to show that. The about the complementary part. So that's the multi-object spectroscopic redshift that really deal with this population of relatively bright galaxy at intermediate redshift. But here the redshift distribution is much flatter, and of course we found many high redshift galaxies. So the thing also is that the VUDS is, according to the author, one of the most dense. It found 60,000 galaxies by square degree. But if you compare this with only 2 galaxies in our field of view, so we are completely in a different regime. And for doing ultra-deep spectroscopy follow-up or complementary to the HST or to the next generation, which James Webb and so on, Muse is going to be interesting. And that's to give you only the Lyman alpha distribution in magnitude, and you see where we're going. So to conclude, so in only 4 equivalent nights of observation of Hubble Deep Field with Muse, we have multiplied by 10 the number of measured spectroscopic redshift that we obtained with a lot of telescope time. We have observed nearly flat redshift distribution in the redshift range of 3 to 6. We have reached such a completeness of 50% at this magnitude. And we found a large population of Lyman alpha emitters, fainter than HST detection limit. And we also get spatially resolved kinematics of 20 galaxies just in that field. So in 4 equivalent nights of observation with Muse, I think we have just demonstrated that HST can go deeper than the VLT can go deeper than HST, which I think is good. So what's the next? So the paper has been submitted this morning. It will be on AstroPH Monday. All data products will be released to the public when the paper will be accepted. That means the data cube, the catalog, all the spectral and line emission. There's a lot of science to be done. Of course, we are going to play as well as with the data. Lots of things can be done. Search for extended emission. We've started global property, of course, luminosity function, resolve kinematics. We are going to still improving the data reduction because we are in the early phase of the project. And we also been working on the advanced data reduction and data analysis software, how to deal with this big data cube. So fishing in this big data cube is nice, even a bit addictive, but it's time consuming. So we need to define, to work on some tools to do that better. So what's next? The UDF, of course, is an obvious target. It's a part of the GTO. So we have started. We are currently accumulating observation on this. So we are doing the complete 3x3 arc minute at something like 10 hours or a bit more depth. And there's one field we are going to push much more, probably to 50 hours. And this is the one where there will be ALMA deep observation. And I think it will be nice, very interesting to look to the complementary. And in a few years, 2017, we'll get the adaptive optics facility. The spatial resolution will be boosted by 50%, which means that we can do the same type of work at 0.5 arcsecond resolution, or 0.4. And it's going to be nice. So maybe another public deep field. Just also to mention, we have 2 postdoc positions. If you want to join the venture, you're welcome. And there's many things other to do, and you will certainly enjoy with Muse, going from a massive survey of a globular cluster with millions of stars that you can resolve in this dense environment to nearby galaxies and even planetary nebulae and many things. Thank you.
So, any questions?
So, comment and question. First of all, congratulations on the extraordinary result. The fact that the line algorithms go up so steeply past the HST suggests that when you this at some strong lensing clusters, for example, you can see something really interesting. Because if the count slope is very steep, which is what your data says, then lensing wins and it pulls a whole bunch of stuff up from the phantom lensing visibility. So that's going to be really neat. Now, question: do you have, I don't know if you computed this yet, do you have a sense of the density of line altimeters as a function of redshift in this sort of redshift? Because you know, there's a lot of furor about whether the density of line altimeters is somehow falling down as we go sort of towards redshift 6 or past.
Yeah, of course.
Do you see anything about that?
Not yet. I think we did a bit more statistics. This is something obviously that we want to do, if we want to see if we can find that. This is something we'll be looking at. I just want to, this is a bit not completely sure because of course here we put the undetected HST all on the same beam. There could be a bit, so maybe not like that, but maybe. But it's clear that it's very steep.
Okay. Any other question? All right. I think we can simply thank you again. All right. So we are now open discussion. I know everybody's tired there. But I would like just to point out that there have been some, we've seen today in the latest days, some results that somehow have been conflicting. So there might be probably a chance here to clarify whether there are conflicts that cannot be solved, or there maybe are issues that we have to look better into it. So I don't know. I just dropped down a few topics. Of course, I mean everybody's free to add more if they are. So for instance, I realized that there have been different statements about the environment. We